Hi, welcome to my video on atomic masses. Hopefully by the end of the video we'll be able to explain why carbon-12 is used as the standard measurement of relative mass. We'll be able to define the terms relative isotopic mass and relative atomic mass, be able to calculate relative atomic masses, and we'll be able to work out relative molecular masses and relative formula masses. So, how would you go about weighing something that you cannot see? This is the situation with atoms. Instead of finding the mass of atoms directly, we compare the masses of different atoms using the idea of relative mass, so in proportion to something else. The carbon-12 isotope, also written as 12C, has been chosen as an international standard for the measurement of relative mass. An atom of the carbon-12 isotope is made up of 6 protons, 6 neutrons and 6 electrons. The mass of an atom of carbon-12 is 12 atomic mass units, 12U. All atomic masses are measured compared with the mass of a carbon-12 atom. Atomic masses are measured using the unit called Unified Atomic Mass Unit, or U. 1 U is a tiny mass, 1.6 times 10 to the minus 27 kilograms. So, a bit of history for you. Why do we use carbon-12? Before 1961, oxygen was used as the standard for atomic masses. It was used rather than the lightest atom, hydrogen, because oxygen combines with many substances to form oxides. Unfortunately, chemists have based their scale on naturally occurring oxygen, which has a mixture of the different isotopes oxygen 16, 17 and 18. However, physicists had chosen the single isotope oxygen 16 on which to base atomic masses. This gave 2 different sets of atomic masses. In 1961, chemists and physicists finally agreed on a compromise. All atomic masses were to be compared with the carbon-12 isotope. Relative isotopic mass is the mass of an atom of an isotope compared with 1/12 of the mass of an atom of carbon-12. All the atoms in a single isotope are identical. They all have the same mass measured against carbon-12. For an isotope, the relative isotopic mass is the same as the mass number. So, for oxygen 16, also written as such, the relative isotopic mass equals 16.0. Note at this point we've made 2 important assumptions. First, we have neglected the tiny contribution that electrons make to the mass of an atom. And secondly, we've taken the masses of both a proton and a neutron as 1.0 U. Most elements, however, contain a mixture of isotopes, so we're going to look at that next. Relative atomic mass, also known as AR, is the weighted mean mass of an atom of an element compared with 1/12 of the mass of an atom of carbon-12. Most elements contain a mixture of isotopes, each in a different amount and with a different mass. We use the term weighted mean mass to account for the contribution made by each isotope to the overall mass of an element. The contribution made by an isotope to the overall mass depends on 2 things. Firstly, the percentage abundance of the isotope, so how common it is. And secondly, the relative mass of the isotope. Chemists then combine together the contribution from each isotope to arrive at the relative atomic mass, AR, of an element. All masses are relative to the mass of carbon-12. So, now let's do a worked example. A sample of bromine contains 53% of bromine 79 and 47% of bromine 81. Determine the relative atomic mass of bromine. So how are we going to do this? We're going to work through it in steps. Step 1. Calculate the mass. In this example, it's very easy. We're already told the mass. We're told the mass of bromine 79 is obviously 79, and bromine 81 is obviously 81. By mass, we're talking about the atomic mass, not to be confused with the previous slide talking about atomic number. They are different. So, the atomic mass is the same as the mass of an atom. So, it would be the number at the top. The second step is converting any percentages to decimals by dividing those values by 100. Third step, we multiply the mass of each isotope by the proportion of the element in the sample. And lastly, we add the values together. So let's try that then. We had 53.0% of bromine 79 and we had 47% of bromine 81. So the relative atomic mass, AR, for bromine equals 53.0 divided by 100 times that by 79 plus, same again for the bromine 81, so 47 over 100, that's 47.0, over 100 times 81. So that leaves us with 41.87 plus 38.07, which equals 79.94. And that is our relative atomic mass. So, relative molecular mass, also known as MR, is the weighted mean mass of a whole molecule compared with 1/12 of the mass of an atom of carbon-12. So, the key difference there between the relative atomic mass and the relative molecular mass is the molecule part. It's talking about more than one atom now. You can find the relative molecular mass by adding together the relative atomic masses of each atom making up a molecule. So, for example, let's do Cl2, chlorine. The relative atomic mass of a chlorine atom is 35.5, and we can see that on the periodic table. There are 2 atoms of chlorine in the molecule, so we do Cl times 2 to Cl2. So that gives us 35.5 from here, and we times that by 2, and that gives us 71.0. And that is our relative molecular mass, MR. Compounds with giant structures do not exist as simple molecules. These include ionic compounds, such as sodium chloride, and covalent compounds, such as silicon dioxide. Although the term relative molecular mass is often used for these compounds, a better term is the relative formula mass. So it's the weighted mean mass of a formula unit compared with 1/12 of the mass of an atom of carbon-12. You can find the relative formula mass by adding together the relative atomic masses of each atom making up a formula unit. So, for
for example, we are going to take calcium bromide, CaBr2. The relative formula mass we can find out using the relative atomic masses. So, relative atomic mass for calcium is 40.1, 3 significant figures. And as we found out before, the relative atomic mass for bromine is 79.9. So now let's work out our relative formula mass. So we are going to take that 40.1, 3 significant figures for calcium, and we're going to add bromine to that. So we have 2 atoms of bromine in this molecule. So we're going to times that by 2. 2 times 79.9. And that gives us a relative formula mass of 199.9. Definitions are often asked for in exams, so you could be asked to recall definitions for the relative isotopic mass and the relative atomic mass. You should not be asked the key definition for the relative formula mass. Today we have learned why carbon-12 is used as the standard measurement of relative mass. We've defined the terms relative isotopic mass and relative atomic mass. We've calculated relative atomic masses, and we can also work out relative molecular masses and relative formula masses.